All right. Hello and welcome everyone to the next installment of our webinar series, today featuring guest speaker, Professor Galan Moody, who'll be presenting a talk entitled Recent Advances in Integrated Quantum Photonics. My name is Garrett Cole, and I'm the manager of Thorlabs Crystalline Solutions in Santa Barbara, California. And as a collaborator of Galan's, I take great pleasure in moderating today's webinar. Galan is an associate professor in the Electrical and Computer Engineering department here locally at the University of California in Santa Barbara. Prior to joining UCSB, Galan was a research scientist and formerly NRC postdoc at NIST in Boulder, Colorado. Additionally, he was postdoctoral associate at the University of Texas, Austin, after receiving his PhD in physics from the University of Colorado, Boulder. Professor Moody is a recipient of an Air Force Young Investigator Award and an NSF Career Award, both in 2021. He serves as a Thrust co-lead and is also on the executive committee for the UCSB National Science Foundation-funded Quantum Foundry, chairs program subcommittees for several conferences, including Frontiers in Optics, as well as CLIO, and is on the editorial board for PRX Quantum and IOP's Journal of Physics Photonics. Throughout Galan's talk today, please feel free to submit any questions that you may have using the Q&A tool, and these questions will be answered following the presentation. So at this time, I'd like to hand things over to Professor Moody.
Great, thanks, Garrett. Appreciate the introduction and the opportunity to present some advances in integrated quantum photonics and also a little bit more of a focus on some of the research that we're doing in my group. So just expanding a little bit on the introduction that Garrett gave. So I came to Santa Barbara in 2019, so I've been here for about 5 years. And a little bit of what drew me here to Santa Barbara was not just the beautiful campus and the coastline, but also the fact that we have a really nice nanofab facility with really great tools that allow us to do all of the research that we're doing in my group. And it's really well staffed, and so the tools are up and running all the time, and that allows us to fabricate the devices that I'll be talking about throughout this talk. And then we also then bring those devices over to our lab on campus in Henley Hall. It's a fairly new building with a number of optics labs in the building. And we do a lot of characterization of then all the devices that we fabricate, that we design and fabricate. So in my group, we kind of have a few different focuses. A lot of it is sort of under the umbrella of integrated quantum photonics. Sort of our bread and butter is making quantum light sources. And so that's a lot of the focus of what we do. And then we use those for a few different types of applications related to, for example, quantum sensing. And we also make slightly more complex circuits for different applications in quantum. And so in this talk, I'll probably focus mostly on our development of quantum light sources and then some of their applications toward the end of the talk. So just to kind of orient you on a brief outline on what I'll be presenting today. So I'll give an introduction, a few slides on integrated photonics for quantum information, some recent progress, why we even care about integrated photonics for quantum applications, and then I'll start diving into the main materials that we use, which are compound, semiconductor, and insulator, so 3-5 materials. I'll then present some of our work on generating entangled photon pairs using integrated photonics, using this 3-5 platform, and then some newer results from the group on multiplexing and multi-photon entanglement. And then I'll dive into an overview of a couple demonstrations. So the first one is with entanglement-based quantum communications. And then the second one is through collaborations with John Bauer's group and Nexus Photonics here in Santa Barbara, integrating chip-scale lasers with our pair sources. Okay, so let's just dive into sort of an introduction and a background of the field itself. So the idea of quantum photonics is pretty old. So that, is decades, probably more than 60 or 70 years old now. It's sort of the quantum theory of light. But thinking about integrated quantum photonics, it's actually a fairly new field. This graphic here shows a timeline that I would say, this field probably began around 2008 or so with some very basic demonstrations, right? So something just like 2-photon interference, which is fairly routine now. If you kind of advance, from 2008 all the way up to, a little bit more recently, within the last couple of years, we have much more complex integrated photonic circuitry. And so we can do things like multi-photon entanglement, boson sampling, integration of many quantum emitters with integrated photonics, using integrated photonics to interface with other quantum systems like trapped ion systems or neutral atom systems. And so even just in the, the past 15 years or so, the componentry and the performance of those components have advanced quite dramatically to enable really interesting applications now that are that many groups around the world and companies around the world are pursuing. And I would say a lot of this has been enabled by the mature CMOS process, so basically silicon microelectronics and leveraging that process for integrated photonics. So this is sort of my one slide background in integrated photonics for anyone who isn't as familiar with integrated photonics. The idea is it's sort of the analogy of microelectronics and routing electrons around a chip. We're doing the same thing by routing photons around the chip. And you can do that by taking some high refractive index material like silicon and surrounding it by a low refractive index material like silicon dioxide. And if you do that, then you can confine an optical mode in the silicon material, and then you can design circuits to guide that light around the chip. And with silicon made in different foundries, you can integrate many different kinds of components. And so you could have a waveguide and put metal above the waveguide, and that metal can serve as a heater to tune phases through thermo-optic effects. You could have things like grating couplers to couple light onto the chip and off of the chip. You can make different types of modulators. You can integrate detectors. And so there's lots of different kinds of components that can be integrated in a really sort of scalable, manufacturable process. And I think that's really been one of the driving factors for integrated quantum photonics. Most groups, at least initially, began and still work on using silicon. So if we think about scaling, looking at the number of components that have been integrated on integrated photonic chips, integrated photonic circuits, you sort of have the equivalent of Moore's law for integrated photonics. And so for classical photonic integrated circuits, you can see a number of trend lines here. And I can highlight this one, for example. This line here is for heterogeneous integration of 3,5s on silicon, for example, indium phosphide or gallium arsenide. And you can see there's upwards of 10,000 components or so that can be integrated on a single chip. We also have an analogous sort of trend for chips that are designed for quantum applications. And so just this past year, or maybe late 2023, upwards of 2,000 to 3,000 components integrated onto a single chip to do certain applications. And so there's a number of challenges with utilizing integrated photonics in sort of a useful way for quantum applications. One is scalability, and this isn't just the number of components that you can integrate on a chip, but it's also sort of the loss of each of those components. It's the crosstalk between different components. It's the reliability and things like that. So it's not just the number of components, it's really the quality as well. And then compatibility among different materials. And this is important because typically one needs to think about different functionality, and different materials may offer better performance advantages for different components or subcomponents. And so, typically one can't think of just using silicon or just using other materials like the 3,5s we focus on or silicon nitride. You have to think about hybrid or heterogeneous integration of lots of different kinds of materials. And so how are they compatible with each other? And to give you just one concrete example demonstrated last year, so this is work that came out of Bristol and some researchers from PsiQuantum and PKU and others published in Nature Photonics. So what they had demonstrated was very large scale integrated silicon quantum photonics. And so they were able to integrate 2,500 components onto a single chip shown here. So there's a large 200 millimeter wafer fabricated at a foundry. And then if you keep zooming in, you see the chip that they used. And this has something like, I forget the specific number, but something like 32 quantum light sources and lots of different interferometers and beam splitters. And they are going this route because they want to do something like generating multi-photon entanglement at as high rates as possible. And so this kind of tells you the state of the art in terms of the number of components on an integrated photonic chip. And so then I think this kind of opens up the question of how do we scale from sort of a few qubits or a few photons with entanglement engineered between the photons to something that's a little bit more useful, a useful quantum system. And I think there's a really nice analogy if you think about sort of microelectronics from 1946 with vacuum transistors to VLSI in the 1980s and sort of the integrated microelectronic chips that we have now in all of our electronic devices. There's a very similar sort of parallel track that quantum technologies and quantum photonic technologies in particular are also taking. And I think that, this opens up the question of how do we go from something like a quantum advantage to some tasks that aren't as useful to something like a really useful quantum system. And so we're probably, in the sort of 1950s or 1960s right now, related to microelectronics. And so it's how do we push beyond that and really have sort of large scale systems that are very useful. And I think this is one of the advantages of photonics. And if we think about what is, a useful quantum system, in this particular example, a quantum computer, going to look like in the future, it's not going to be something that's small. It's going to be huge. It's going to be in a warehouse with many connected modules or server racks of different components and different technologies. And so I think that this is one of the advantages of any sort of quantum platform that uses optics, because then optics naturally allow you to network all of these different racks and modules together. And so here's an example of a graphic from PsiQuantum, for example. So they show all these different server racks, and they're connected by optical fibers, and some of them are cryogenically cooled, some aren't. There's lots of different componentry. And so you're networking many modular devices, and each device has sort of special functions to perform certain computations or storage or detection and things like that. And I think fundamental to this is that one needs to be able to distribute entanglement across all these different server racks. And so having really good quantum light sources that can generate entangled photons at really high rates with really high quality is sort of paramount for being able to do anything like networking quantum systems. And this could be for quantum computing. It could be for quantum networks more generally. It could be for quantum communications, quantum sensors. The ability to generate high quality entanglement at high rates is a really key component to be able to do all of that. Okay, so with integrated photonics, there's a lot of different materials that one can choose to try to make quantum light sources. And in the next sort of section of this talk, I'm going to discuss how we actually generate quantum light. But I want to motivate that by looking at the different materials that one could choose from. So I mentioned silicon photonics earlier. The way we're generating quantum light is using nonlinear optics. And so one would want to pick a highly nonlinear material to use for generating quantum light. And so in this chart here, I'm not going to go through it in detail. It's just highlighting some of the different material parameters for different materials that have been developed for integrated quantum photonics. And I really want to highlight the 3-5 materials. And the reason we have been interested in the 3-5 materials is if you look at the optical nonlinearity, so the second order Chi2 nonlinearity and the third order Chi3 nonlinearity, they have some of the highest optical nonlinearities of any of these materials. So higher than silicon, higher than lithium niobate, for example. And so it's a matter of pushing that technology to leverage that high nonlinearity, make low loss materials, low loss devices, and then we can start to do something really, really useful. So that's a lot of what my work and my group and others have been focusing on, is trying to advance the 3-5 material platform for quantum photonics because of this fundamentally high nonlinearities of the materials. So if you're interested in sort of looking at a comparison between different materials, there's a number of reviews that my group with collaborators have put out in the past few years, and they're referenced here on the bottom. And so feel free to look through those. If you have questions, emails are on those papers. You could always email me or other corresponding authors, and we can provide any information if you're interested. Okay, so that kind of nicely leads into the next segment of this talk in terms of how do we generate entangled pairs using integrated photonics, and then discussing some of the advances that we've been pushing with this platform in the last few years. Okay, so how do we generate entangled pairs? There's many ways to do this. One could use two-level systems like quantum emitters, semiconductor quantum dots, atoms, and so forth. For a lot of our work in my group, we focused on using nonlinear optics. And so the idea is not necessarily new. Nonlinear optics has been around ever since the laser's been around. And so, we're just leveraging existing ideas and concepts and technologies for quantum applications. And so you're probably familiar with nonlinear optics in a number of different ways. One of the coolest demonstrations is second harmonic generation. So for example, taking like a 800 nanometer TISAF laser, sending it through a nonlinear crystal like BBO, and generating 400 nanometer photons coming out. So you can actually see the blue light, the second harmonic light that's generated. And that's a Chi2 nonlinear process, a second order nonlinear process. There's many other types of nonlinear processes. One other common example of that is green laser pointers, for example. They typically are actually a red laser, so a 1064 nanometer laser, and then there's a nonlinear crystal in there to double the frequency. And so then you get, red conversion to green light that comes out of your laser. And so those are two key examples. We're basically doing the same thing with our integrated photonic chips. And so up here on the top left, this is sort of a very simple schematic of what's really kind of, going on in the devices that we're making. So you take some sort of nonlinear material that either is a Chi2 or a Chi3 nonlinearity. If you shine a laser on that material through either spontaneous parametric down conversion, so taking one of the pump photons, it interacts with the material and it can convert into two new photons, typically called the idler photon and the signal photon. And these photons are actually going to exhibit some level of correlations if you design the experiment properly. And those correlations can be non-classical, and that's where we get the entanglement out from these processes. There's also another way to generate entanglement, and that's through what's called spontaneous four-wave mixing. So that's a third order process. So in this case, we take two pump photons incident on the crystal, and those two pump photons will be annihilated, and through conservation of energy and conservation of momentum, they're going to create two new photons at slightly lower frequency and slightly higher frequency, signal the idler photons, and those photons will exhibit some level of entanglement. There's different ways to create different types of entanglement. I'm not going to get into a lot of detail about the different types, but I just wanted to point out that there's, for example, polarization entanglement, which I think is probably what's more well studied and understood. And so you can configure this kind of system to produce entanglement or correlations between the polarization of the signal and idler photons. They may come out and they're both horizontal polarized or they're both vertical polarized, but you don't know which the polarization the photons are. So that gives you some level of entanglement between the polarization of the photons that come out. There's also time energy entanglement that one can produce. And so there's correlations in when the photons come out and their energy or their frequencies. And that's typically what we're using in my group, is producing time energy entanglement. Okay, so to show you a couple images of kind of what these things look like. So on the top left is kind of going back to this diagram of what the photonic waveguide cross-section would look like. So this is the optical mode that can be confined in the waveguide. So we are using 3,5 materials like aluminum gallium arsenide or indium gallium phosphide. And then we surround that with silicon dioxide. And so we have this fully clad with silica that confines the optical mode into the 3,5 material. And we want to make sure that we're confining that optical mode as tightly as possible into that material, because we're using nonlinear optics. We want the mode in the nonlinear material to enhance that conversion efficiency. So on the bottom is an SEM image of what this structure could look like. And so you see the sort of rectangular feature. This is the 3,5 material. Down here is the silica. Up here is vacuum. This is before we then deposit before we deposit silica to fully clad the system. So then we can make structures that look like this one here on the in the center. So these are long spirals. This is anywhere from 1 millimeter to 10 centimeter long waveguides on the chip, and then we just spiral them to make sure that the chip size is not too large. And then we also make devices that are microring resonators, so the figure on the right. And so what happens in this example is we have a waveguide on the bottom. If we inject laser light into that waveguide, it's going to propagate along in the right direction. In this region right here, some of that light is going to couple into the microring resonator and start circulating around that microring resonator. And depending on the loss of that resonator or the quality factor, that'll determine how many times that light is circulating around. And that gives us a very large effective interaction length of the pump light with the material itself. So as the pump is propagating around the microring resonator, it's converting into signal idler pairs, and then we're extracting those signal idler pairs out of the waveguide and then off the chip, and then doing experiments off the chip. So these are sort of the two different examples of either waveguides or resonators that one can make to generate these entangled photons using nonlinear optics. So to give you a little bit more details about the microring resonator, so these devices have been developed also for classical photonics, so for creating frequency cones. And so if you look at, for example, the spectrum coming out of this device on the right-hand side here, if you pump this resonator hard enough, what you get is a frequency cone coming out. So In this particular example on the top, we're pumping just above 1550 nanometers. We turn up our laser power and we start to get photons at all these different comb lines. So in this particular case, this is a 1 terahertz comb. So the spacing between each of these lines is 1 terahertz. About 7.5 to 8 nanometers. And then we can get a comb that spans upwards of a couple hundred nanometers. If we turn down our laser power, then all these lines start going down, and it's a little bit harder to measure on our optical spectrum analyzer. But we want to operate in a regime where we're not producing many photons, we're producing just a few photons at a time. And if you turn the pump laser down, then analyzing the photons at each of these different frequencies, at each of these different comb lines, we can actually show that they are indeed entangled. And so in the experiments, what we do, if I remind you, spontaneous Fourier mixing is we take 2 of these pump photons at 1 frequency, they get annihilated and converted into signal annihilator photon at higher frequency and lower frequency. So what we can do is we can send light off the chip here and then basically look at the photons, for example, with the 2 stars, or the photons at the frequencies with the 2 triangles, and look at their correlations. And from analysis of those photons, we can show that those ones are entangled. And what I want to point out is that the rate at which we can produce entanglement at these particular frequency modes scales as something like the nonlinearity squared. And so we want to have very highly nonlinear material. And also this is normalized to the mode area. So we want to confine that mode to as tight of a waveguide as possible. It scales as the quality factor cubed. So that's like 1 over the loss cubed. And so we want to have as low loss material as possible. And then 1 over the radius squared. And so we want to make basically the mode volume as small as possible. And so it's really a matter of trying to optimize all of these at the same time. And that is pretty challenging. One could dramatically increase the quality factor of devices by making really thin waveguides and pushing the mode way out into the really low loss, like cladding material. But then that comes at the expense of the nonlinearity. The effective nonlinearity would go way down because now your optical mode is not interacting as much with your nonlinear material. It's interacting with the cladding that doesn't have the high nonlinear coefficients. So there's trade-offs in terms of really enhancing all of these at the same time in order to try to enhance the pair generation rate as much as possible. So that's a lot of what we've been focusing on the last few years. Okay, so how do we make these things? So let me kind of walk you through a little bit of this process. So we start with a silicon wafer, and we work at 100 millimeter diameter, so 4-inch diameter wafers here at UCSB. Most of our tools are sort of set up for 4-inch. So we take a 4-inch silicon wafer. We have 3 microns of silica on top. And then we also have another wafer that is our 3.5 wafer, and we can design that 3.5 stack based on whatever sort of applications we're particularly interested in. And so this is typically just like gallium arsenide, some sort of etch stop material, so a high aluminum concentration AlGaAs, a lower aluminum concentration AlGaAs, or this could also be indium gallium phosphide. And then we often are doing a thin alumina layer right on top. And then what we do is we just do flip chip bonding, or we do wafer bonding. And so we're going to use plasma activation on the 2 surfaces. We're going to press them together. We're going to heat them up a little bit, and that develops bonds. Right? So we can do this at chip scale, and my group is typically doing this chip scale here at UCSB. If we want to go to wafer scale, we've collaborated with Thorlabs Crystalline Solutions, led by Garrett Cole, and we get really nice sort of wafer scale bonds here. And so you can see here on the bottom, this is a 4-inch wafer of silica oxide, and then the green thin film, that's 102 nanometer thick indium gallium phosphide, for example. And you can kind of see really high quality, high uniformity across the entire wafer. And so then we'll take that wafer, or the chip on top that we fabricate here at UCSB, and then we do some additional processing. So we've removed the substrate, we've done some passivation. We can then deposit additional silica for full cladding. And then we can also metallize either on the side or on the top. We can put metal on the side if we want to make things like electro-optic devices, or we can put metal on top if we want to make tunable devices using thermal optics. So just passing a current through that metal heats up this local region, and we can create sort of phase shifts to make tunable elements of the waveguides below those heaters. So that's sort of a quick overview of this fab process. And if you are interested in this, we're happy to discuss more and share information. a lot of this information is also publicly available, published in our papers. We have a paper on the archive as well on the indium gallium phosphide process with a lot of details there. Okay, so some nice images of, okay, what do we get out of this? We end up getting a wafer of devices here. We'll then dice up these wafers and we get lots of chips that then students are very happy because they have lots of measurements they can do, and they get to test all of the devices that they've designed and modeled and laid out and fabricated themselves. And nice images of a number of students in the group Lily, for example, looking very happy with her nice wafer that she's just fabricated. Okay, so then what we do is we bring these devices back to our lab to do all the testing. And so on the bottom, for example, I'm showing you one of these chips that we've diced up. And in this case, there's arrays of a ton of different quantum light sources where we're sweeping lots of different parameters, maybe the radius of the resonator or the waveguide widths or the gap between this waveguide and the resonator right in this region. We can sweep a lot of different parameters, especially when making these at wafer scale. This allows us to do huge parameter sweeps. And then we can compare sort of screening all of these devices and the results from that screening to our simulations to make sure that what we're simulating is accurate. And so then we can do lots of measurements, and showing here, for example, there's a red laser here that's used for the alignment of this fiber V-groove array, so a multi-channel fiber array to the integrated photonic chip. And then we'll turn off that red laser, turn on our telecom laser to do entanglement generation with 4-wave mixing. So then what we'll do typically is we'll pump at like one frequency, and then let's say we're interested in looking at entangled photon pairs at these two lines here. So this would be like our signal and our idler modes. So we'll couple light off chip, and we'll go through sort of standard telecom fiber-based filters to basically filter out everything and demultiplex these photons. And so what we can get are these photons into one fiber channel and these photons into a different fiber channel, and then we'll send those into our single photon detector system. And so in our group, we're typically using superconducting nanowire single photon detectors as a commercial system, and in this case from Photon Spot, a very nice system, sort of a nice package system. You can get your detectors, you can get your fridge, the cryogenic electronics, the readout electronics and amplifiers and everything, so it's kind of a nice turnkey system. Pretty high detector efficiency, pretty good timing jitter, and this allows us to do all the experiments that we want to do. So we'll send idler photons to one detector and signal photons to the other. And then we'll use time taggers, so high-speed electronics to record when are we getting photons on each detector, and that allows us to put timestamps on all of that, and then analyze the quality of the photons that we're producing. Okay, so I'm not going to go into details on all of those measurements. I kind of want to just give you a summary of those measurements. And so these two figures are kind of a summary of that. So the one on the left here, this is the detected signal counts on just one detector as a function of the amount of 1550 nanometer laser power we're putting on chip. And so we see a nice sort of quadratic scaling as expected, because this is a 4-wave mixing process, so it scales as the power squared. And so as we increase the power, for example, up to about 100 microwatts of on-chip power, we're producing something like 10 million photons per second. And this is what we're detecting. And then if you look at the coincidences, so when I get a click on my signal detector, do I also get a click on my idler detector? And in principle, you always should, because when we produce these entangled photons, we're always producing them at the exact same time. And if we had zero loss in our entire system, then we'd always get a click on both detectors at the same time. But of course, there is loss in the system. There's a little bit of loss in terms of getting light off the chip, and then we go through filters, which has a little bit of loss, and then the detectors aren't 100% efficient. So there's always a little bit of loss. So what we really care about is trying to maximize this rate of coincidences. I want to click on this detector and this detector at the same time, because that means that we've kept both of those photons, and now they're both useful. And so if you look at the detected coincidence rate, we're on the order of about 1 million per second detected photon pairs with, on the order of 100 to 200 microwatts of on-chip pump power. And just to give you a little bit of context to that, if you look at commercially available sources, so these are just 3 that I dug up. I think there are also more, but quickly looking through their specs, if you look at their pair generation rate, for example, for this periodically pulled lithium niobate waveguide, it's on the order of about 30,000 pairs per second. Another design from Oz Optics, you get almost about 1 million pairs per second, spread across a pretty broad bandwidth. And also another one based on fibers. So forward mixing fibers, and you're on like, around 1,000 pairs per second. And so if you look at these rates, these compare quite nicely to existing commercial sources. And so we're starting to work on packaging these devices and making them sort of deployable and more field ready in the coming year. Okay, so maybe to put that in a little bit of context. So in this plot here, I'm plotting then the brightness. So this is like the number of pairs per second within a normalized bandwidth. And so typically what we do is we normalize that to like 1 gigahertz. And so we could produce a ton of pairs per second, but it's over a really broad bandwidth that may not be as useful, because in your real experiments, you often have to put in filters. And those filters are going to filter out all those photons and just get rid of them. And so you want to produce as many photons per second as you can in a fairly narrow bandwidth. And so if you plot the brightness and then also the Bell state fidelities, this is kind of a nice metric of the quality of the photons that you're producing, our results are kind of up here. And then that compares to, for example, silicon and silicon carbide and lithium niobate and so forth. And so, the performance is quite good for the 3.5 materials, kind of as expected. This kind of opens up a question though. Okay, so why just stop at 1 ring? We have pretty good results from 1 resonator. So, this is kind of what I've shown, right? We have 1 resonator coupled to 1 waveguide. And if we just look at what's coming out, we have, sort of a pump at 1 mode, we get a signal here and an idler here. So why not just put more on there, right? If we put more on there, you could do something like this. We could put a bunch of rings on 1 waveguide. We can kind of tune them using thermal optics to align all the different rings. In this particular example, I'm showing 3 rings. Now, if we have 3 rings, we can pump all 3 of them, and then we can start filling in all this empty space in the frequency domain. We can start filling in that with all these different resonances and really use this multiplexing to increase the throughput, increase the total summed rate of photons that we're getting out of the devices. Okay, so that's exactly what we did. So one of my students is testing these devices right now, and in this particular case, we have 20 resonators on 1 waveguide. These are not necessarily coherently coupled to each other. These are sort of independent resonators. This is really just more, let's just multiplex. We're already pumping 1 waveguide with 1 laser with 1 ring. Let's just put a bunch of rings on there, pump them all, and then take out all of the photons from that 1 waveguide. So if you look at 1 ring, we're producing, a photon spectrum that looks something like this, right? And this can span upwards of 200 to 300 nanometers. If we look at all of the rings, then we'll have something like this. So this on the bottom is a transmission spectrum. We basically send the laser light into the left, we couple the laser light out on the right, and we measure the power, and then we sweep the laser frequency, and you see a spectrum that looks like this. Each time you see a group of modes here, this is because you're coupling into one of those resonators, and so you have a little bit less transmission at the output. So you can see we have very nice groupings of all these different modes here. Each one of these groupings corresponds to about 20 different lines corresponding to 20 different resonators. And so this is kind of a nice proof of principle. Okay, we make this device, we have all these different modes. Now what we want to do is we want to go and pump, for example, like right around 1550, we want to pump all of those modes and then produce signal photons here and idler photons here and analyze all of those different modes. If you kind of work through all the numbers, you can get some advantages for multiplexing with upwards of, okay, if you integrate 20 rings and look at the entire broadband spectrum, you might get something like gigahertz rates. So going from sort of megahertz or million photons pairs per second detected to something like 1 billion pairs per second detected. Okay, so my student has been working on this. For example, right now he's focusing on 5 rings. It's a little bit easier than doing all 20 initially. So if you look at the plot on the left, what he's done is he's tuned 5 of these resonators such that they have very nice, precise spacing. And so we now have these groups of modes here, here, and here. And if we zoom in on the central set of modes, then we have these very nice sort of 12.5 gigahertz spaced modes. So these are 5 different rings. We've tuned them to have 12.5 gigahertz spacing. And then what he does is he takes his laser and he sends it through an electro-optic modulator off chip, and that basically produces a cone, right? And so now he can take his CW laser and also then get power at each of these modes. And so his modulator is also set at 12.5 gigahertz. And so then we can send that light in and basically pump all of these different pump modes and then produce idler photons here and signal photons here. And he's doing quite a bit of analysis now on understanding what are the detected signal rates for all the modes, what are the coincidence rates, what is the crosstalk, what is the quality of entanglement, and so forth. And the results are pretty encouraging. Kind of as expected, you get about a factor of like 5 scaling. So if we can produce 1 million pairs per second that we detect on our detectors, now we can get like 5 million per second because there's 5 rings. Okay, so we also do some other sort of types of circuitry. So it's not just resonators, but now looking at other kinds of components on the chip. For example, the one on the top, this is an on-chip Honglu Mandel interferometer. And so I'm not going to go into details on exactly what's going on here. It's just kind of showing the sort of complexity at which we're fabricating devices. This is nowhere close to what people are doing in silicon with 2,000 or 2,500 components. It's a little bit less mature of a platform in that sense. We're not trying to scale to trying to put thousands of components on chip. It's more of saying, can we add in some advanced functionality to add in some tunability for our pair sources? I kind of have the viewpoint that you can try to put as many components on chip if you want, but eventually you still have to get that off chip. And if you think about long-term using these devices for quantum applications, you really have to think about it in sort of a modular way. We're not going to integrate everything onto the same chip. We're going to have to connect lots of different modular chips using fiber optics. And so we focus on developing the key core technology that we know how to develop, and then try to interface these different chips together. That's kind of the approach. On the bottom is another design to create multi-photon entanglement. For example, entanglement between 4 different photons at the output. Okay, so I'm going to kind of skip this summary because there's a couple demonstrations I kind of want to walk through, and I want to make sure we have time for questions. So this is just kind of a high-level summary of everything I've just talked about. But I want to kind of leave enough time to talk about a couple more recent experiments that we've been working on. So I'm going to go into a couple demonstrations. The first one is on entanglement-based quantum communications, and then the second one is on integrating lasers. And so right now we're using bulk tabletop optical laser systems, which are very nice and very good, but also very big and expensive. And so we want to see if we can reduce the footprint and the cost of those. And that's mostly through collaborations. Okay, so for the first one, we were thinking, what is the first demonstration that we can do with these high rate sources? And the easiest thing that we thought of initially, it turned out to be a lot more complex and challenging and took a lot longer than expected, as research often goes. But was quantum communications. And so just to kind of walk you through what we're trying to do and why we care about using entangled photons for quantum communications, here's an example of like a classical communication RSA encryption scheme, right? Alice wants to send some sort of encrypted message to Bob. She can take her message, she can use what's called a public key to basically encrypt that message, send it over to Bob over a public channel so someone could come in and steal that information, but it's encrypted. And then if Bob has a private key that is in some way related to the public key, he can then take that encrypted information and decrypt it, right? The challenge is if there is an eavesdropper, current encryption, these methods are secure right now, but the concern is if and when quantum computers become powerful enough, are they going to be able to then crack this sort of encryption process? And will our encrypted data be secure? And that is an open question right now on whether that will happen or not. And so there's a lot of work to motivate, how do we actually generate these keys in the first place in some sort of secure way? How can Alice and Bob share these keys that allow them to encrypt and decrypt these messages in a secure way that's guaranteed by the laws of quantum mechanics? That's the motivation for quantum key distributions. It's a matter of trying to create these keys, which are really just bit strings of zeros and ones, random zeros and ones that only Alice and only Bob know. And so that's the motivation for QKD. Okay, so that was one of the motivating applications for using this kind of source. So what we can do is we can take the photons that are coming out of this device, we can send it through sort of commercial fiber-based DWDM filters. This basically takes the comb of all these different frequency modes and separates them into different fiber channels. And then we can send photons to all these different channels. So to like Charlie, Alice, Bob, David, and so forth, depending on the number of frequency modes. Okay, so I'm going to walk you through what this scheme is. And I'll skip over some details, but I'll try to explain this as clearly as possible. So let me just kind of set this up. So we've got our pair source here. We have our laser that we then use to pump the source. We're sending in photons, through this waveguide port here, generate pairs in the resonator, couple them off the chip, and then we go through some commercial fiber-based DWDM filters. This allows us to send idler photons to Alice and signal photons to Bob. Okay, and then at Alice and Bob, they each are going to have some components to allow them to try to generate these. First, we generate pairs at a central node. And then Alice is going to take the idler photons, and she's then, if we just focus, for example, on this Z basis here. So she's going to take these photons, she's going to have one detector. So the photons arrive, she'll get a click whenever a photon arrives at her detector. And so then she's going to record when she gets that click, but then she's also going to add an electronic delay. She's basically going to make a copy of her electrical signal and then delay it by some delay tau. Bob is going to do the same thing. He's going to take his signal photons, but instead of having sort of this artificial sort of 2 bits here with a delay, he's going to use an optical system. So he's going to use 2 detectors. So when his photon arrives right here, this is a 50-50 beam splitter. It could either go to detector 0 or it could go to detector 1. It's going to be one or the other. Detector 1 has an optical delay tau. This is the same delay as the electrical delay that Alice has. Okay, so that's setting that part up. Then what they do is over a classical public channel, they're going to announce all of their detection times publicly, and they're going to look for coincidences. And one may think that this completely destroys any sort of security because they're announcing when they detected their photons, but it doesn't. And so let me kind of walk you through what that looks like. Let's go like event by event. Let's say we produce a signal idler pair. We send one to Alice, one to Bob. Let's say Alice detects at time t1, some random time t1. Well, because these photons are created at the exact same time, she's going to get t1 and then this artificially delayed t1 plus tau because she's making a copy of her photon. Bob's photon, when it arrives, could either go to 0 or to 1. So let's assume it through this 50-50 beam splitter went to detector 1. So then he is going to get a click on his detector at time t1 plus tau, right? Because these photons are created at the same time. And so then if they, over a public channel, look at timestamps, they're going to both know that they have a photon at t1 plus tau. And that's on what they call their detector 1. So they now would record, okay, we got 1. Okay, then the next time a pair is generated, let's say that's at some random time t2. Alice will then have t2 and t2 plus tau. Let's say Bob's photon again went to this detector. So he's going to also get a click on his detector at time t2 plus tau. So they both share this common time t2 plus tau. That's another bit 1. And then you can kind of keep doing this. And let's say the next instance, Bob's photon went to detector 0. So that would be time t3. So that's the time that they share and so forth. So you can do this continually over and over and over again. And the key security lies in the fact that these times, t1, 2, 3, and so forth, look like random times to some sort of eavesdropper. And so no one is really going to know what these correspond to in terms of 0s, 1s, except for Alice and Bob, because they both have this common time now. And so that's exactly what this protocol is doing, using these time energy entangled photons. We have deployed a fiber across our campus. It's running underneath one of the main roads on campus, looping back into our lab, and we're sending these photons across this fiber to test out this protocol using sort of fiber in a realistic setting. This is nothing special about this fiber. This is just a standard telecom fiber. And we have rates that are quite good, quite high compared to other chip scale sources. Okay, so details of this work is also published later last year in Optica Quantum. You can look through this algorithm as well as our approach using integrated photonics. Okay, in the last few minutes, I'm going to skip this and kind of, this kind of goes into scaling and how high rates we might think we can get. I do want to talk about a second demonstration, and this is using integrated photonic sort of chip scale lasers to pump our sources. And this, I think, is a really interesting direction to go into because, right now we think, okay, there's some level of scalability by taking sort of bulk tabletop optics, putting them on an integrated photonic chip, and we get really high quality, high rate entangled photons out. but we still need a lot of these other control electronics, especially big bulky lasers, to pump the devices. And so if one can get around that, then one can really make more of a nice packaged turnkey laser and pair source. So it's kind of taking these bulk tabletop optics and trying to put it into an integrated photonic system. So here's a nice image of one such chip that's designed and fabricated and developed by Nexus Photonics, which is a local startup company here in Santa Barbara. And so this chip, for example, to give you context of the size, it's about 5 millimeters long. This is 3.5 gain material on silicon nitride, so it's heterogeneous integration. And here, I think there are 15 different lasers on this one chip. And so you're seeing the red here. This is because we're just pumping, electrically pumping this one laser and then coupling light out of the chip here and into the fiber here. So right now, we can then take that light from that chip into the fiber and then send that fiber over to our other discrete component, our integrated chip, and generate pairs that way. So in this past few months, we've done a lot of characterization of these devices. One of the main things we wanted to do is to see if we could actually get mode hop-free tuning of these devices. And so if you look at the bottom left here, this is just the lasing spectrum of two different types of chips. And so each chip has about 20 nanometers, or each laser has about 20 nanometers of coarse tuning. And so you can tune anywhere from around 770 to 785 or 790 nanometers, or they design the gain material a little bit differently. You can also tune all the way up to close to 800 nanometers. We wanted to develop sort of mode hop-free tuning, at least over a certain spectrum, in order to make sure that we could sort of precisely tune and map out the resonances of our integrated photonic devices. And so that's a lot of the work that one of my students, Josh, has been leading in the past 6 months or so. And so we just posted a paper on the archive about how to actually get pretty good mode hop-free tuning up to about 100 gigahertz. So we do coarse tuning, 220 nanometers, mode hop-free tuning at each one of those positions of about 100 gigahertz. So if you're interested in more details of that, there's also a paper on archive now on that. And so then we did a couple demonstrations. And so in our group, in collaboration with John Bauer's group, for example, we're using this to pump silicon nitride resonators that are designed for entangled pair generation in the visible around 800 nanometers. So you can see on the bottom here, here's a transmission spectrum of one such resonator. You can see we get really nice sharp dips and we get really nice spectra from these mode hop-free lasers. Also in collaboration and work that's led by David Weld's group here at UCSB, they have a rubidium vapor cell setup. They use this laser to basically pump their rubidium vapor, and they can map out like the D2 transition, the D1 transition. They can see the hyperfine features, and they also locked to those different features. So they can do absorption locks of this laser onto the different transitions in the rubidium vapor cell. So it's a really nice versatile tool. Right now they're all discrete components, and we're working on thinking about packaging these together so we can have a really nice turnkey laser quantum light source and something that's really easy for anyone to use. Okay, so to conclude the talk, I kind of want to maybe think a little bit forward in terms of additional advances needed to really push forward quantum photonic integrated circuit technologies. Something I'm interested in is understanding, can we even further improve the efficiency and brightness of the quantum light sources? Can we get another 1,000 times improvement over what we've already achieved over silicon, for example? And so I think there is a path towards doing this, and it's kind of going from what we've talked about with Chi-3 nonlinear photonics to Chi-2, so down conversion. And we've been pushing a material platform to do this. This is indium gallium phosphide on insulator. We have a paper out on the archive about the fab process on this. Here's a very nice wafer of lots of devices across the full wafer fabricated by my student Lily. This is also in collaboration with Garrett at Thorlabs for the wafer bonding and fab development. We're also interested in broadband pair generation, so not just at like 1550, for example, but 1 photon at telecom and 1 photon anywhere throughout the visible. So we've been working on some modeling and simulations of that. So we have a paper also out on the archive on that. And this is work that's led by an undergrad in my group, and she's done amazing work on the modeling and simulations of that. And then there's a number of other sort of technologies and components that I think are important. I do want to point out one that I think is really important is low loss packaging. So getting photons off chip is fairly painful. And can we push this to something like 0.1 dB, chip to chip fiber coupling, and do that reliably? That's something that I think would be pretty transformative. You know, we're starting to see some results of this from some larger companies. The question is, how reliable is that? How far can we scale that? Will that be useful for different kinds of materials like 3.5s or heterogeneous materials? So that's something that I'm very much interested in seeing how far we can push that. Okay, so to make sure we have enough time for questions, I'll just conclude, all the different funding agencies, also a list here of all the collaborators that we work with. I just want to thank them, and then shout out to the fab of our way here. And yeah, happy to answer any questions.
All right. Awesome. Thank you, Galan, for that excellent and informative presentation. We have a few questions in the chat there. I'd like to invite the audience to continue submitting questions, although we will be slightly limited in time. Perfectly, you covered a lot of these topics in the summary, but I'll start from the earliest question. So a user asked, is there merit to integrating low-loss waveguides for, say, specific low-loss transmission components of the integrated circuit, and then, say, tapering or shaping the waveguide to increase confinement for enhancing the nonlinear interaction? So sort of like optimizing the waveguide for certain positions in the chip.
Yeah, no, I think there is actually a lot of merit to doing that. That's just kind of thinking initially, like just doing that in one material platform might be challenging, because then typically you have to like change thickness and things like that. So I think the best approach to do that is to do heterogeneous integration, and that is something that we are starting to work on with collaborators, for example, with Nexus Photonics. So basically taking like low loss silicon nitride, and then where we want to do pair generation, we convert from the silicon nitride to the 3.5, get the light that's generated, get it back into the low loss silicon nitride. I think that that's probably the best direction to go long term. Fab's harder. So there are technical challenges of doing it, but I think long term, that's the right way to go.
No, that's a good one. I would also, just to re-summarize, like how do the losses compare in the 3.5 waveguides compared to like a silicon nitride or an oxide-based waveguide or silicon?
Yeah. So if you compare like similar designs for like quantum light generation, the 3.5s are better. But if you just say, okay, what is the absolute loss? Like when we're designing our 3.5s for quantum light generation, you know, our best is around like 0.2 dB per centimeter, but routinely like below a dB per centimeter loss. That's fine, but yeah, if you want to make something kind of complex, then you want to beat that down a lot more. And so like the best silicon nitride, I mean, it's like, you know, sub dB per meter. So, you know, 3 orders of magnitude better. But those aren't very good designs for quantum light generation. So combining both of those, I think, is actually a good way to go. I think it's even more than that, though. It's not just the propagation loss, because we're not propagating over a lot of material, right? And so these devices are pretty short. And so what's actually more important, I think, is the chip to fiber coupling. And because of the lower refractive index of silicon nitride, I think the designs end up giving you much better coupling into optical fibers, right? So some of the best designs have, you know, I've seen below 0.4 dB, you know, chip to fiber coupling with silicon nitride. And so that's kind of a bigger motivating factor for why we want to have heterogeneous integration. Is I don't think we'll be able to hit that kind of chip to fiber coupling loss with just the 3.5 without like a crazy amount of redesign or work. And so we want to leverage everything that's been developed in silicon nitride and just put our 3.5 at the spot we need it, and then that's it.
Yeah, no. Since this connects to something you just mentioned, I'm going to jump out of order for a second. So someone asked specifically about the losses in and out coupling onto the chip. What sort of numbers do you see there? And then does this have negative impacts on things like the QKD demo that you discussed?
Yeah, that is also a good question. So our best is slightly below like 3 dB for getting light off chip. So we're losing about half, which I think is like, it's pretty standard. I think if you look at like what you can get from a lot of like other foundries, that's kind of like typical. It's not the best though. Like I said, I've seen below 0.4 dB. You know, for example, like PsiQuantum is starting to quote way better numbers. They're sort of in the milli-dB or hundreds of milli-dB. I don't know sort of the scale of that. That's what you get out of a foundry. And we want to basically take that kind of technology and say, okay, like, let's not try to do that in the 3.5s. We're never going to do that. So let's try to then take our 3.5, get efficient coupling between the layers, but then leverage what's being developed in the other platforms. So yeah, we're like around 3. If we get 3 dB, we're happy. But
is that typically
loss all along the way loss all along the way, whether it's chip to fiber coupling or filters or detectors or whatnot. For QKD, that's going to ultimately limit then what is your entangled like bit per second, like what is your entanglement rates. So that's going to limit your key rates. So lower loss means more usable photons, your rates are going to go up.
Yeah. And then staying on that topic, is it typically grating couplers, edge coupling? How are you doing that? And then on the fiber side, is it lensed fibers, single mode, multi-mode? What just additional technical details if you can share?
Yeah, we've made both grating couplers and edge couplers. We typically are sticking with our edge couplers. Fundamentally, if you look at like the simulations, they're pretty similar in terms of performance. The edge couplers are a little easier to use, so that's typically what we use. For us, we have custom setups. We don't have sort of any turnkey automated setups, commercial setups for testing. So we made everything custom for our experiments. So we do edge coupling, and then we are using lensed fibers and trying to basically do mode matching between the mode that's coming out of our waveguide and the lensed fiber to get as good coupling as possible.
Great.
Yep.
Switching gears a little bit on the more like materials and wavelength side of things. Right now, obviously for propagation and fiber, these things are carried out 1550, and for low loss propagation. There was a question about, performance of single photon detectors may not be as optimized at 1550. So should more effort be put into enhancements on the detector side, or shifting these systems to shorter wavelengths where you may have higher efficiency detectors?
I don't know if I agree with that assessment of the detectors. So I think some of the most efficient single photon detectors based on the superconducting nanowires are at 1550. If I recall correctly, the number that comes ahead is like to my head is what NIST's demonstrated. I think their best detector was like above 98 or 99% efficiency.
And that's like you said, for the single photon or the nanowire superconducting detectors.
Yeah. If you want to use like, APDs, for example, then InGaP APDs are noisier. The efficiency is not as good as silicon. The silicon APDs around like 700 to 800 nanometers are much better. But
I think I assume that's where the question was coming from.
Yeah. So in that case, like, there is merit to maybe doing that. There's a lot of interest in free space communications, in quantum communications, and there I think 800 nanometers is actually a better wavelength. If you do a full analysis, and there's some groups who've done some very nice analysis on everything with diffractive optics and atmospheric turbulence and all of that, 800 nanometers might actually end up being a better wavelength to work at. And in that case, you can also use the silicon APDs.
Yeah, but like you said, with the super high efficiency superconducting detectors, assuming you can deal with the large footprint of the detector, you can work.
So it's going to be application dependent in terms of what makes the most sense.
Yep. 1 second. Then there was another question about on the component side, like if you're building a 50-50 beam splitter on chip, how good does this have to be? Is it plus or minus percent level, or do you have to get like 10 to the minus 4 sort of splitting ratio?
Yeah, that is a good question. We want to get that as close to 50-50 as possible, and as good extinction. Like for making an interferometer on chip, we want to have very nice extinction. And it depends a little bit on the application, what you're trying to do. You can make like a Mach-Zehnder interferometer on chip with as close to 50-50 beam splitters as possible. That'll give you demultiplexing if you design it right. So you can send your signal in this waveguide and idler in this waveguide. If you start deviating from 50-50, then sort of the extinction ratio goes down, the crosstalk goes up a little bit. So you really want to try to get that as spot on as the 50-50 as close as you can. I wouldn't say though we're at like this, sort of within a percent level. Like, if we are at 49 and 51, like that's typically fine. So it doesn't have to be that precise, but the better you can get it, the closer you can get it to 50-50, the better.
Yep, nice. I'm going to go fit in 2 more questions if we can. So one is a just very fundamental question about, and let's see if you can summarize this quickly. Like, how do you verify the time energy entanglement? Is there a brief description of how that can be realized?
Maybe. I'll try to make it. There's a couple ways that one could do that. One thing that you can initially do is measure what's called like the joint spectral intensity or the joint spectral amplitude. You can also measure time correlations. What we do is we measure the quality of time bin entanglement. So we have time energy entanglement. And then what you do is if you send your photons through an unbalanced interferometer, just like a fiber-based interferometer, you can then look at the counts coming out of that interferometer on your detectors and sweep the phase. And then you can see these oscillations in the interference. And depending on the visibility of those oscillations, that then directly relates back to what is your entanglement fidelity. And so that's one of the main ways we do it, is basically using unbalanced interferometer. It's called Franzen interferometry. And if we do that and measure the visibility, that's how we can figure out the quality. And so we can do that with like 99% visibility, which is basically like, you could think of it as like 99% fidelity, more or less.
Yeah, nice.
Yep.
Cool. I'm going to end with one more general question. So sort of a future-facing thing here. Yeah. So in your opinion, how far are we from having everything integrated on the chip, like source, all the passive components, tuning the resonator, so on, detection side? Like, what is the outlook for full integration of all these components?
Yeah, I guess like I would say like now one can do that now. I think, for example, like bigger companies like Quantum and even like Xanadu or quantum computing focused companies could do that now. And I think Quantum has showed results where they are doing that now. But I think it really depends on the application and whether you want to do that or not. We, for example, don't really want to integrate superconducting detectors on our chip because then we have to cryo cool it down. It's not as useful. I'm very much interested in laser plus source, package that. So I could just hand this box to someone. They can plug in some electronics and they get a ton of entangled photon pairs out. So I think it's very application dependent in terms of how much do you really want to integrate on chip. And that's kind of why I harp on the better chip to fiber coupling. I think that's overall a better approach. You get some advantages for full on chip integration, but only of some components. You're still eventually going to have to get light off chip to make these things useful. So
yeah, I like
do it now, but
I like that first response, right? I mean, in principle, it's possible now, right? But it just depends on what you need. So
right.
Yeah. Cool. Yep. All right. Well, we will close it out. Thank you, everyone. That was really nice, dynamic questions. So thanks for contributing, and thank you, obviously, Galan, for the wonderful presentation. I will note that on September 18th, we're going to have another webinar, this time on a very different topic, miniature 2-photon microscope from the Thorlabs imaging group out of Virginia. And be sure to register for this event by clicking the Register Now button below or on our website at thorlabs.com/webinars. Hope to see you again soon. And thank you, Professor Moody, for that fantastic presentation.
Thanks, Garrett. Thanks for hosting. Appreciate it. Thanks, everyone.